As promised on Monday, we're going to come back and look more closely at fractions, and that's what we're going to be doing today. We're going to do kind of like a workshop here for the last 20 minutes, 25 minutes of class, where I'm going to go over a couple of things and have you try a few problems, and then we'll go from there. So we're going to look at fractions. And if you recall from Monday, we talked about the fraction having the numerator and the denominator. So 3/4, of course, the 3 is the numerator, and the 4 is the denominator. Well, the 3, the numerator is really a count. It's telling us we have 3 of something. And that 4 is a name, telling us what it is we have 3 of. Just like 3 inches or 3 cows or whatever. So the first thing we need to do is we need to figure out what does it mean to have a name of a fourth. And the easiest way to describe that, or to define it, is to go back to the old elementary school definition of a pie or a pizza. Pretend that looks like a circle, by the way. That is cut into 4 equal pieces. While you're at it, pretend those look equal. And the 3 means we have 3 of those pieces. So the 4, the fourth, means that each whole object gets cut into 4 equal pieces. Or you could look at it from the other side, that it takes 4 of those pieces to make one whole object. Now we had mentioned that we need to be able to rename those fractions. The easiest way with this illustration to rename it is probably to cut them into other slices. Let's cut each slice of this pizza into 3 other slices. Again, pretend that these are equal. Now, how many total slices does it take to make a whole pizza? 12. We had 4. We cut each of them into 3, so 4 times 3 makes 12. How many slices do we have? 9. Good. We had 3. We cut each of them into 3 slices, so 3 times 3 makes 9. So we now have 9 twelfths. Well, do we have any more or less than we did before? No. What we have there is the exact same amount. 9 twelfths and 3/4 are the exact same amount. It just looks different. The reason they're the same amount is what we did right here. We multiplied by 3 on the numerator and the denominator. In other words, we multiplied by 3 over 3. What that's saying is it takes 3 pieces to make a whole object, and we have 3 of them. In other words, we have 1 whole object. So we just multiplied by 1. And in math, anytime we multiply by 1, what does it do to a number? It stays the same. It does nothing to it. This is what we refer to as a unity fraction. And a unity fraction is equal to 1. The numerator and denominator have the same value. And throughout math, unity fractions are used a lot to change the name of a number. Here it's to change the denominator of a fraction. For a measurement, it can be used to change it from feet to inches, or inches to feet, or whatever. Those unity fractions are used to change the name. Now here we just picked that 3 out of thin air and we multiplied it by 3 over 3. Well, usually what's going to happen is we'll have something like 2/5, and we'll be told that we need that denominator to be 35. What did we have to multiply the 5 by to turn it into a 35? 7. There we go. So if we multiply the denominator by 7, what do we have to do to the numerator? Times 7. So 2 times 7 is 14. So now once again, 14/35 has exactly the same value as 2/5. Or we might have, let's do 2/3, and I want to change it into 15ths. What do I have to multiply by to turn thirds into 15ths? 5. So I have to multiply by 5 on top as well to get 10. So 10 15ths. So what I want you to do is in your big book, you open up page 42 here. And actually it's page 43. On the very bottom of page 43, we are renaming those fractions to the given amount. Like 1/2, I want to rename it as 16ths. So what I'm going to do is I'm going to give you about 2 minutes here to work through as many of those as you can get. 1 through 11, 1 through 12 is what's listed there, but just do the odds. 1, 3, 5, 7, 9, 11. And we'll talk about those in just a couple minutes. Okay, so for number 1, 1/2 becomes how many 16ths? 8 16ths, good. Number 3, 3/4 will become 24 30 seconds. Number 5, 7/8 will become 28 30 seconds. Number 7, 11 16ths, 34 64. And number 9, 1/4 by 20. And number 11, 19 12ths, 144. Number 7. Yes. Now you might recognize that as being an improper fraction. We will talk about those in just a minute. Okay, so we can change the name by enlarging them like that. But if we can multiply the top and bottom by the same thing, or multiply by a unity fraction, if I wanted to take this 10 15ths back to a simpler fraction, like 2/3, now first of all, why do I call that simpler? Well, the human brain, when it visualizes stuff, can really only visualize between 7 and 13 things at once. So trying to visualize that it takes 15 pieces to make a whole object, your brain struggles with that in many cases. So 2/3 is just a lot easier to visualize. So to take it back, we would just reverse this process. Instead of multiplying by 5 over 5, we're going to divide by 5 on top and bottom. 10 divided by 5 is 2. 15 divided by 5 is 3. We've already established that 2/3 and 10 15ths are the same amount. Now again, here we multiplied it by 5, so we knew that we had to divide by 5. The trick is looking at a fraction and figuring out what you can divide both the numerator and denominator by. If we have something like 15 over 25, what can I divide both of those numbers by? 5. So I'm going to divide 15 divided by 5 is 3, and 25 divided by 5 is 5. So you do get 3/5. Well, looking at numbers, sometimes it can be tricky to figure out what each of them divide by. So there is something out there called divisibility rules. To tell if a number can be divided by 2, what do? The last digit is even. In other words, the last digit is 0, 2, 4, 6, or 8. So if I have a number like 2,794, all that matters is that last digit is even, it's a 4, so we can divide by 2. Anybody tell you divide by 3? Multiples of 3, yeah, but is there a quick way to look at it? 3s and 9s. Okay, there it is. The sum of the digits. So if we look at something like 2,700 and, let's do 54. If I want to tell if that can be divided by 3, I'm going to add the digits. What is 2 plus 7? 9. 9 plus 5? 14 plus 8, or plus 4 is 18. Is 18 divisible by 3? Yes, it is, yeah. It'd be 6. If I didn't know, I could do 1 plus 8 is 9, and I know 9 is divisible by 3. So yes, that number, since the digits add up to something divisible by 3, the whole whole number is divisible by 3. Now there is a rule for 4, but it really doesn't matter. It's a difficult one that doesn't work well anyway. So let's go for 5. How can you tell if something is divisible by 5? The last digit is 5 or 0, 0 or 5. How about 6 again? There's a rule, but it's not very convenient. Anybody know a rule for dividing by 7? Neither do I. As far as I know, there isn't one. If you come up with a really good one that works every time, show it to me, and I'll give you extra credit in the course. Then I'll publish it. Get rich and famous. I wish. 8 has one as well, but again, it's not really worth using. It requires you to memorize your multiples of 8 up to 1,000. We're not gonna go for that. 9 is the same as 3, sum of the digits again. So our 2,754, those digits added up to 18, is that divisible by 9? Yeah, so that would also be divisible by 9. How about 10? Last digit is 0. So if I'm looking at numbers to see what they can be divided by, the first thing I usually look for is 10. It's really easy to see if it ends in a 0. Then I'll look for the 5. If it doesn't end in a 0, maybe it ends in a 5. After that, I usually jump down to 2. Is the last digit even in both of them? And if it is, well, then I know I can divide by 2. Or then the last thing I would look for is 3, just because that process is a little more complex. If none of those work, then you actually have to try dividing out like 7 and 11 and stuff like that. Now, there is a divisibility rule for 11 and a lot of your other, what they call prime numbers as you get larger. Those divisibility rules get so complex as the numbers get bigger, they're really not worth mentioning. So if I have something like, let's see here. Let's do 90 over 210. Well, when I look at both of those, the first thing I see is that both of them end in 0. So I'm going to divide by 10. What's 90 divided by 10? 9. What's 210 divided by 10? 21. Now, as I look at those, I can see both of them can still divide by 3. 9 divided by 3? 3. 21 divided by 3? 7. Many of us were taught that you have to find the largest number that divides into both of them. That greatest common factor, they call it. That's not true. You can find any number, divide it out, and then look again. And it might take more steps and more time, but you can keep working. I find it's a lot easier once the numbers get a little bit smaller to figure out what goes into both of them anyway. So what I want you to look at next in your book on page 44, halfway down the page there where it says exercise 2-5. 1 through 12 again, I want you to do the odds, 1, 3, 5, 7, 9, 11. Reduce each of those like we just did by finding what both numbers divide by. Now, number 1, 2 8 reduces to 1/4. Number 3, 6/16. 3 8. Number 5, 90 over 80. 1 1/8 or 9 over 8 for now. Number 7, 7/28. 1/4. 9, 48 over 64. 3/4. Good. And number 11, 81 over 36. 9 over 4. Or yes, some of you may have reduced it to 2 1/4. Okay, so the next step is just what we saw there. We had 9 over 4. That's an improper fraction. It's called improper because we don't like having the numerator. That pen is we don't like having the numerator bigger than the denominator. So what we prefer to do is take it out and figure out how many whole pieces we can get out of it and how many pieces are left over. Kind of like what we looked at on Monday with a division and a remainder. In fact, that's exactly how we can do it. 9 divided by 4. Well, 4 goes into 9 how many times? Twice. 2 times 4 is 8, so there's 1 left over. So this is 2 with 1/4 left over. We might have something like 44 over 7. So it's the same thing. 44 divided by 7. How many times does 7 go into 44? 6. 6 times 7 is 42. There's 2 left over. So that's 6 with 2/7 left over. Notice the denominator always stays the same, doesn't change. We're just breaking it down to see how many whole objects we get out of it. So in your textbook on page 46 I want you to do 13 through 24 there, just the odds again, so 13 through 23. Break those down from improper fractions into, this is what we refer to as a mixed number. So convert them from improper fractions to mixed numbers. Okay, so from 13, 14 fifths becomes, better big ones. Hold yourselves back. 2 and 4 fifths. 15, 43 fourths will become 15 3 fourths. 17, 79 sixteenths will become 4 and 15 sixteenths, good. 19, 87 eighths. 10 and 7 eighths. 21, 318 over 32. 9 and 15 sixteenths or 9 and 30 32nds. Either one would be fine. 451 over 64. 7 and 3 64. Now we need to go the other way. If I have a mixed number, like 2 and 3/4, and I want to turn that back into an improper fraction, what we have to do is break these whole objects back into pieces. How many pieces are each of them going to be? The denominator tells us how many pieces. So each of those 2 whole objects is going to be broken into 4 more pieces. So we have 2 times 4 becomes 8. So that becomes 8 pieces. We had 3 pieces before, so we're going to add those 8 to it. 3 plus 8 is 11 over 4. So 2 and 3/4 becomes 11/4. So if I have 5 and 1/3, what I need to do to break up the whole object into pieces is 5 times 3. The whole number times the denominator. What's 5 times 3? 15, and I add that onto the numerator because those are the pieces that are already there. What's 1 plus 15? 16. So that's 16/3. Make sense? Okay. We are at our time, so what I want you to do is just a couple of problems of homework. Starting on page 45. It's that exercise 2-7. It actually goes over onto page 46. 1 through 11, the odds. Should take you all of about 2 minutes to do, and that'll be it for us for today.